AI workflows means a lot of different things to a lot of different people, as is obvious. And in my 5 minutes of fame, I'm going to take a very specific perspective on AI workflows. I think Timo has a shared but broader perspective, and namely that is AI-coupled HPC workflows. And a lot of this is done as part of the ExaWorks project you've heard Kyle mention. Okay, so bringing us all onto the same page as to why should we worry, be interested, concerned about AI-coupled HPC workflows. And there's not enough time to get into the details, but just to appreciate through this set of figures that when you can couple AI methods with traditional HPC workflows, you can do bigger, better, faster. It doesn't come easy, it doesn't come for free, but it is the beginning of what I think, and happy to hear other opinions, is going to be a profound change in which computational science is done in years going forward. This is just a specific example of the protein folding problem. Again, a lot of effort has been spent into this, and shows you that if you can get AI models, in this case, convolutional variational autoencoders, to guide and steer your simulations, in this case, hundreds, thousands of ensembles running on large machines such as Summit, you can do better than traditional vanilla simulations. And when I say better, I don't mean a few percent, 10, 20%, I mean orders of magnitude. And that's best seen by this bottom, on the bottom side of the left graph, or the right graph for that matter, where you see 2 or 3 orders of magnitude difference between the red and the green, right? And that's just to say you get to the experimental results in far less computational and thereby wall clock time. So clearly, this is just one simple early example. The field's proliferating with very innovative ways in which AI couples to simulations. And again, I know Timo has some very nice, even more powerful examples. Another example to keep in mind as to why to think about coupling AI to HPC workflows is this particular, very profound result of finding a drug candidate. This is part of the DOE's National Virtual Biotechnology Laboratory involving Argonne, Brookhaven, Oak Ridge, and many others, Livermore. And this is just one of the many strands of the NVBL, but it, in my opinion, did something quite remarkable. It came up with this drug candidate in order few months of computational time. 100 billion candidates going through a fairly rigorous pipeline with input to downstream experiments, which is where the actual drug candidate was synthesized. Now, people have been doing drug discovery, molecule recognition for years, and this is one of the staples of the pharma industry. But to be able to get through a very large space in very short computational and physical wall clock time is something that, in my opinion, was possible only because of the coupling of AI methods with traditional HPC methods, coupling at the docking level, coupling at the binding free energy level, so on and so forth. Lots of details in the paper, but I hope by the end of this slide, if you weren't to convert into believing that if you're going to do scientific discovery in the 21st century, you're going to have to rethink your computational processes, you are a convert now. Okay, so trying to connect this to some of the structures and the goals of the community forum. Remember, this is not a research talk. This is trying to see how we as a community can get together, do things. Benchmarks, try to understand use cases, try to share best practices, more than that in a short while. We're just trying to start building up the terminology of things that have kind of happened since the last meeting about a year ago. Is yes, AI couples to HPC in many ways, but let's start building a common vocabulary and terminology. And at least this is one, by no means complete, by no means the last, by no means the best. But it is trying to say that you can couple AI with HPC in ML, AI, X, HPC, where X could be in, out, and about. Won't bore you with the details, but I think some ways, alternative ways of thinking about this, which again, Timo has nice discussion, is inner loop and outer loop, but this kind of complements, gives you a different perspective. again, Raphael set this up very nicely, start talking about motives, talking about patterns. And after a careful analysis of about 30, 40 papers, really burgeoning dynamic field, there are at least 6 workflow patterns, motives, execution patterns, I must hasten to add, because motives could be for different things, but these are execution patterns. And here are the listing. And interesting to see that the first 5 are really ways in which workflows, HPC workflows, use AI. And the last is a nice example of where a workflow is used to create the AI model, which in turn might then be used to steer simulations or be used with simulations. But the point here, again, this is not complete. This is not necessarily entirely finished, and definitely by no means the best. But this is the kind of activity which hopefully we can think together and grow and do better, rather than all of us doing this in silos, to help the community move towards the enablement and adoption of AI-driven workflows at a more, if you will, scalable and sustainable level. Then just try to kind of see from my perspective, and Timo and I will work on this together, is kind of just start thinking of the challenges, hopefully the discussion of the benchmarks, the discussion of the kind of 3 different modes of coupling sets up the obvious statement that there's a lot of underlying research that needs to happen. And I won't get into that here. This is not a research talk once again, but try to focus on the latter 2, the subsequent 2 points, the software tools and shared infrastructure. Kyle talked about this, Raphael mentioned this in passing, many different partial solutions, but they're not always easy to extend or interoperable. This is an area that is growing. It's in its early days, so I think I'm optimistic, and I believe that as a community we can get together and get ahead of some of the developments, and for once try to see if we can kind of prevent this proliferation, this Cambrian explosion that inevitably always happens, if we can at least manage it, if not prevent it. And again, referencing the various activities that we said in our first community forums and summits about benchmarks, data sets, and sharing best practices, 2 modest activities that have actually taken place as part of a DOE Oscar project, been trying to take some of these benchmarks, and many of you will know about ML Commons, which is the industry standard and academic standard for all things related to machine learning, benchmarks, profiling, so on and so forth. And Jeffrey Fox leads the science working group of the ML Commons work activity. He, along with Tony Hay, have helped try to take one of these motives, the one that I have on the previous page, and try to say, okay, we're going to embed this in this community activity. And so this is actually hopefully a point for discussion, that the activities that the Workflows Community Summit is fostering, engendering, at least some parts, the AI part of it, should align possibly with what is now the community and industry standards, namely ML Commons, and just some activity there. And there's more obviously happening. I've provided a reference to that project for those in the bottom left and right hand corner for those who might be interested. And maybe just a thought. We talked about, Kyle and Raphael talked about a technical paper. I think this is an area that is ripe for a technical paper, and possibly a sub-working group to try to meet in the interstitials of the broader summits to try to both advance the technical papers, but also to try to evolve the benchmarks, data sets, and best practices. I'll hand over to Timo. Sorry for going a couple of minutes longer.
Yeah, so I'm going to show a little bit of a different workflow as an example, and I apologize for those who've already seen this at SC, but we felt it was actually interesting to bring this up again, because maybe this falls under Raphael's comment of, well, workflow is everything and nothing, right? Everything is now a workflow, and we keep seeing different patterns. But I would argue that this is actually very closely related, though also very different. And so I thought for this forum, it would be useful to, again, for the people who weren't able to attend SC, to kind of just think about a very different style of, or what I would consider a very different style of workflow that I think actually will become very common, and we should be able to handle as a community. So the background here, I'm going to try to catch up a little bit on time here, but the background is essentially that just about any physics phenomenon that we know, right, we can never actually model it at full resolution, like we can never do first principles. So we end up doing this weird multiphysical, not weird, we end up doing this coupling, right? We solve one equation at some resolution that we think is adequate, and then maybe we need a chemistry reaction that is more trustworthy. So then we call a different piece of physics that actually resolves that chemistry at a higher resolution, or maybe some other physics, right? So maybe we do hydrodynamics versus radiation transport, or transport versus reaction, or clouds versus ice, right? There's many different examples where we end up coupling different physics together in order to kind of make a more complex model at whatever kind of resolution we A, think is kind of sort of trustworthy, but B, we can still afford with the current system of supercomputers. One particular common pattern that we see a lot at the labs, but in other cases as well, climate, combustion, nuclear physics, are what we call subgrid models, where, so I have a little schematic here on the right, where you have some, what I call a coarse grain code running, typically like a hydrodynamics code, like moving your fluids around, that does a large scale time step. And at every time step of the large scale code, at every point in your grid, you need to do some fine scale evaluation. Maybe you do an atomic physics package, maybe you do a chemistry evaluation, maybe you do an equation of state, whatever it is, right? At every point you call this physics module, then you collect all that data, you ship it back to the course code, and you continue. And that is, right? Climate models do this with cloud models, and so we see it everywhere. The problem is, depending on the fidelity of this physics models and the that you call kind of in the inner loop of the simulation, the high fidelity model in the middle really dominates your runtime, because it's just partly because it just gets called so freaking often, right? So now your entire code becomes this trade-off between, oh, I would like my physics to be really accurate. Oh, if I make this twice as slow, right, my code is just going to go die on me. And then the solution the last couple of years, right, has been, hey, we can just build a surrogate model, right? We can build an AI model, which is why this is part of the AI workflow piece. We can build an AI model that maybe is an approximation of the actual real physics, because that's going to be super fast, and we can put that on the GPU, and it's all great. So the advantages there are obvious, right? We would expect a massive improvement of performance, and in fact, people have published a lot of really cool work already, essentially based on that idea. And it's just a version of reduced order models for those people who know that community. The challenges in making such a thing is you need to first collect all your training data. You then need to guarantee that the model that you did build is accurate wherever you need it to be accurate. And if it wasn't accurate, you need a way to fall back, right? You need to tell the auto computation code, it's like, oh, nope, my model just failed and crapped out, like your solution is not accurate. None of these are actually simple. And what currently is effectively done is you first execute your simulation with the original code, as slow as it needs to be. You collect all that data, that becomes your training data. You train a model. There's a whole bunch of different discussion on the ML side about how do you know that that model is reliable, and how is it effective, and how sensitive is it, blah, blah. Let's imagine you actually trained a surrogate model on that data that you collected that actually works. And then you can execute the same simulation with that model much faster, in which case the physicists say, well, what's the point? I already executed it once. I don't need to do that again, right? I already know what comes out. And then you say, well, but I can use the same model for a next simulation that I don't know, except that you don't actually know whether that simulation needs the model in the same way, or it needs something slightly different. And if it needs something slightly different, then your model might fail, and then where you're at. So you end up in this weird kind of convergence loop that says, well, now I learn my new simulation, and I have to test whether I do something that the model doesn't know. And if I do, then I have to stop, and then I have to collect new training data. And so it just becomes incredibly expensive, incredibly time-consuming, and also there's a lot of risk for failures. So what we're trying to do right now is actually build a workflow that addresses this by autonomously managing the model and the model training and the data collection. And again, I'm going to try to go through this quickly. So the idea is to, instead of having a single evaluation on the physics on the left that we saw before, to explicitly split this in a question that says, hey, so we call it UQ, right? Uncertainty quantification. So there's going to be a question that's asked for every grid point that says, do you believe that your current model is accurate enough to answer this question? The answer is yes. Great. I'm just going to use my ML model. It's going to be super fast. Awesome. If the answer is no, I'm actually going to go send that piece of input to another module, might be on the same node, might be on the same call, might be on the same machine, might be on a different machine. I don't care, right? Just going to go send that inputs to some physics server kind of idea. That thing is going to compute the physics for me, and it's going to send the data back. There's a bunch of load balancing involved, like very work-free, it's non-trivial. But what I'm also going to do is I'm going to intercept the outputs. So I'm now having input-output pair. I'm going to scroll that off into some sort of database that now contains my database of training data. And if I get more new data, at some point, I'm asynchronously going to start off a new training. I'm going to update my model, going to potentially validate my model on the fly, and then I'm going to send it back while the simulation is running, kind of update the model. And then the next time the simulation actually tries to do the model, right, it's updated. It knows more. It can adapt to the current situation. So now I can more or less confidently run a new simulation, because if it goes outside what my model currently knows, it's fine. It's just going to slow down again to the speed that I'm currently running things. But if the model is valid, then it's going to be super fast. And now you can build all kinds of really interesting workflows on top of this. For example, there's no need to do this with a single simulation. You could have an ensemble of simulations that all call the same physics server. You could do all kinds of interesting things where now, if you were saying, my model is, I observe that my model is accurate 90% of the time, I can take those 10% and make them 10 times as accurate, right? I can just run a much more accurate physics model because I have that time, right? So now I can run a much better physics simulation. And then, right, there's a whole bunch of workflows. So the right stuff maybe wants to live in a cloud, right? Because it's machine learning and databases and that kind of stuff. The left stuff is clearly an API code. So there's a lot of interesting workflow pieces here, but in a way that I would call an inner loop workflow, right? Something that actually gets called in the inner loop of the simulation, rather than like schedule a whole bunch of long running jobs on resources that are available. So we thought that this would be an interesting example to think about as kind of an extension of what we currently think of as AI workflows.